Thanks.
Okay. Hi, everyone. The Center for Studies in Advanced Computing, the Institute of Mathematics and the Faculty of Engineering of UNAM offer you the warmest welcome to the virtual seminar Blockchains. To begin with this event, we have the presence of Dr. Boris Escalante and Dr. Sergio Raxuamu, who will inaugurate the seminar.
Hello, good morning, everyone. Thank you for joining this seminar. I'm very happy to be here. This is a very unique seminar. Blockchain is a trending topic. Blockchain is changing life in many senses, mostly in the economic transaction field. And I'm very, very happy to know that this seminar has called the attention of so many people. This is not only because of the topic, but also because we have very important speakers, very worldwide known speakers, as Vincent Gramoli. I'm sure this is the reason why we have had so many registrations for this seminar. I think this is one of the very few benefits of pandemic. We wouldn't have been able to hold this seminar with speakers coming from all over the world and attendees who are also disseminated in several places. So I'm very happy to inaugurate this seminar. And I want to thank Sergio Rasbaum, Rocio Maldeco, Armando Castañeda, Alejandro, who's not here yet, for having the initiative to hold this seminar. I'd like to invite Sergio Rasbaum to give some words, to give some welcome and some introduction to this seminar. So Sergio, please go ahead.
Hi everyone. Hi, thank you, Boris, for the introduction. Actually, I don't have much to add. I mean, you already said it very clearly that it's really an honor for me to be able to host this set of very important speakers that are really experts in blockchain. One of the nice things about blockchain is that it has relations with many aspects of computing and even economics and finances. So I'm sure it will be very interesting to hear the different perspectives about blockchains of the different speakers. And I hope also for the students and researchers at UNAM, it will be an interesting event. We have different research groups at UNAM that are interested in blockchains, each one from different perspectives, especially distributed computing, databases, security, and so on. So, I mean, without further ado, let me just start by introducing our first speaker, Vincent Gramoli, who is an associate professor and the head of the Concurrent System Research Group at the University of Sydney in Australia. He has been a visiting professor in Switzerland at the very important EPFL Institute, also working in blockchains. And prior to this, he was affiliated with INRIA, the University of Neuchâtel, and Cornell University. And I think we can start and go ahead. Thank you, Vincent, for agreeing to give this talk, and you can start as soon as you want.
Thank you very much for the nice introduction, Sergio. So it's my pleasure to be here today and to present you how to make blockchain more secure and scalable. What I'm going to do is I'm going to talk about some of the things that we went through when we discovered blockchain for the first time, some of the lessons we've learned, and then some of the solutions or ideas that we came up with in order to improve what we saw, especially from a scalability and security point of view. I just want to mention that, okay, I will talk about that into more details, but the notion of scalability is the idea that we would like to improve or keep some performance as we increase the size of the system. So that's the notion of scalability here that we have in mind. And I want to acknowledge also the fact that all the results that will be presented, or most of the results that will be presented, will be coming from PhD students, postdoc of my research group at University of Sydney, and also research that I've done with great colleagues, included in Lausanne. And yeah, the result is, I mean, what I'm going to be presenting is the result of all these collaborations. So just to give a bit of background, blockchain appeared in 2008 with the famous paper by Satoshi Nakamoto that is called the Peer-to-Peer Electronic Cash System, and that was presenting Bitcoin, the Bitcoin blockchain technology. At a very high level, you can think of a blockchain as a chain of blocks, of course, but that is distributed. And by distributed, we mean that this chain of block is copied across different nodes or machines that are part of the same network. And we would typically refer to the blockchain network as the network that runs this particular blockchain instance, right? So you can have multiple blockchain networks because nowadays we have multiple blockchains, but let's focus on one blockchain and its dedicated blockchain network. We would typically refer to a client as a machine that is expecting a service from the blockchain network. And you can see that here in this representation, you have a set of servers. Okay, these are the machines that are connected and providing the blockchain service. They are connected through the blockchain network. They can communicate using internet with each other. And what we are trying to achieve when we implement a blockchain is to make sure that all these machines have a common view about the current state of the blockchain. So you can see on the right hand side this yellow block that indicates the genesis block of a blockchain, which is the first block that exists in the blockchain. And as time goes on, the more blocks will be appended to this blockchain again and again, and the blockchain will keep growing like this, right? So this is the blockchain abstraction that is replicated at all the servers. Now, the idea is the client can use the service by issuing a transaction, right? So typically in cryptocurrency applications, the client will send a transaction that says, I'm happy to send some coins from my account to Bob's account, right? So I want to pay Bob. So the client will send a transaction to the blockchain network, and some of the machines will receive this transaction in the blockchain network, and they will try to encapsulate this transaction into another block that will get appended to the blockchain. So you can see here that there's a new block on the right-hand side that contains this transaction T that was sent by the client. And now this new block is appended after the genesis block, right? So if there are more transactions coming like that, they can be encapsulated in different blocks that are appended after the blockchain, right? Of course, we can have multiple transactions within the same block, but let's keep it simple. Okay, so there is an interesting phenomenon here, which is, and that is very important, is that all the machines of the blockchain network should agree about what is the current state of the blockchain, right? They should agree that there is this genesis block that is followed by this block that contains T, right? We don't want to have inconsistencies across different views in the blockchain network. As a parenthesis, I will use this left arrow to represent the link between a block and the previous block, because the block that is just appended contains a hash representation of the content of the previous block. So you can think of it as a pointer, right? Okay, so we know that in order for this to work, all the blockchain network machines should agree on the same view of the state of the blockchain. But in the distributed computing literature, we also know, and since 1985, right, so it's not brand new, thanks to Fisher, Lynch, and Patterson, that consensus cannot be solved in the general setting, right? So what is the general setting? It's essentially a setting like the internet, where you cannot really predict the amount of time that a message will take to get delivered, because you have all sorts of congestions, natural disaster, human misconfiguration of BGP routing rules. And because of this, and also because of the fact that some machines may stop working because of some power outage, or you might have some intrusion by a hacker into some machines, and the machines are not may not work as expected. In this setting, you cannot solve consensus, right? So we know this. So now comes the question: how can Bitcoin somehow bypasses this impossibility result to make sure that we have a blockchain that is implemented? How do these machines agree on the current state of the blockchain? So this was an interesting question we asked ourselves when we started looking at blockchain technologies, because essentially, according to the theory of distributed computing, in the general setting, you cannot agree. So it means that for all the machines that are part of the same blockchain network, they may all come to a different decision or a different view of the current state of the blockchain. For example, you could have this machine at the top right corner that believes that the block with this transaction T1 should be appended after the Genesis block. And this other machine at the bottom right will say, no, the block that needs to be appended right after the Genesis block, let's say at index 2, has to be this block that contains T2. Another machine at the top left corner may say, no, it's T3. The block with T3 that has nothing to do with the block that contains T2 that should be appended, and so on and so forth. So you can clearly see that you might have a disagreement based on this theoretical result. And there are possible executions where you would have this disagreement. And if this disagreement happens, then we are in big trouble, because it essentially means that Alice, who said to Bob, I've paid you through transaction T1, actually may reuse the coins that she has used to pay Bob in another transaction T2, for example, right? To use the exact same coin she has used, but to pay Carol instead of Bob. Right, so now we have this double spending situation, and we don't want that to happen, right? We should make sure that all the blockchain network servers agree on the current view. Okay, so let's step back a little bit and try to understand what consensus really means. So consensus, and especially in the Byzantine setting, we say that the consensus problem is the Byzantine consensus, in the sense that even though you have particular participants or nodes in the network that could act arbitrarily, as if they were crashed or as if they were victim of an intrusion from a hacker, all these participants should try to agree on something in common, right? So more precisely, the Byzantine consensus problem can be stated as follows. Consider that each correct node or machine propose a value. This value could be a block in the context of blockchain. The Byzantine consensus problem is for each of them to decide a value such that three properties are ensured. No two correct processes or machines decide differently. Every correct process eventually decides, right? And there is a validity property that says that any decided value is a value proposed by some of the machines that were there. There is also a non-triviality property that says that if all processes are correct and they all propose the same value, then the correct processes decide this value. But it's just to make the problem non-trivial. Now, what is really important is the idea that we want termination. We want all the nodes, machines, or processes, these terms are equivalent here, to agree at some point. Okay, we want the consensus to be reached, and we want agreement, which means that we should not have two machines deciding different things. We don't want to be in the case where where some node says T1 is the block that should be appended after the Genesis block, while someone else say no, it's T2. Right? We want agreement. We want every blockchain network node to decide the same thing. Of course, we cannot impose the Byzantine nodes, the nodes that are faulty, to decide anything in particular. So this is the definition of the Byzantine consensus that we're considering. Now, a few years later, in 2014, an interesting paper appeared, which was the Ethereum yellow paper. So it was written by Gavin Wood. And of course, we need to give credits to Vitalik Buterin also, who contributed to this system. But the system became available the year after, in 2015. And the really interesting thing about Ethereum is that it goes slightly further than Bitcoin. It's still a blockchain, right, system, but instead of just accepting a simple transaction that will transfer assets from Alice to Bob, this system, this blockchain system, allows user to send smart contracts, right? So in this example here, you have the client that instead of sending a simple transaction, it can send a smart contract C, right? So it sends a smart contract that you can see with this red rectangle. And then the blockchain network receives this smart contract C and encapsulate it into a block that gets appended after the Genesis block in this example, right? So it gets appended to the blockchain. Now, the funny thing is that the smart contract is more elaborate than any program you could send in Bitcoin, right? It's not the basic scripting language. It's actually a contract that is written in a Turing complete programming language, right? And so it means that it opens up to a lot of opportunities in terms of programming the blockchain. Once you have uploaded such a smart contract in the blockchain, then another client, it doesn't have to be the same, can invoke a function of this smart contract program, right? So in this example, you have the client that sends C.F. It means that he tries to invoke the function F on the smart contract C. And then what will happen is that all the machines that should have a consistent view of the blockchain, should know about C, right, will execute this function. And of course, we need to make sure that this function is deterministic. So by assumption, let's say that any function of a smart contract is deterministic. Why? Because at the end, we would like the state to be the same if the function is executed on one node or another, right? So anyway, all those machines on the blockchain network will execute the function, and this function may alter the state of some variables in the blockchain, right? And again, we would like to have this consistency that there is a unique block and a unique state that derived from the execution of the smart contract function that is unique across all the network. So we scratched our head and we said, oh, but still there is this problem of disagreement that is possible in the general setting. So how could Ethereum solve this problem? So we looked at the yellow paper and we couldn't really understand how this could bypass the impossibility result. We looked at the code. We went because the code is publicly available, so you can take a look on GitHub about how the consensus is reached. And by consensus here, I'm not talking about a proof of work mechanism or a crypto puzzle, right? I'm really referring to this idea that how can they make sure that all the machines agree on the exact same block at a given index of the blockchain? And then we tried to look at the code and somehow, we used to play with pseudocode or algorithms. So we tried to extract what we call an algorithm or pseudocode representation of what was the consensus protocol inside Ethereum. And we came up with this very simplistic pseudocode representation. And we found out that actually it was not completely solving the consensus, right? Not in a strict way, at least. So this function could be this function of trying to reach agreement consists of proposing a block if you have solved the crypto puzzle, right? You can propose a block for the current index, and then you exchange these blocks and you compare the difficulty of the blocks depending on where they are in the blockchain structure. And then based on this difficulty, you will choose the block that has the highest difficulty, right? And by difficulty here, we mean the difficulty of the solution that was provided to a crypto puzzle. Now, once this most difficult block is found, then this is the one we choose. But if the difficulty between different blocks is the same, then we toss a coin and we pick one of the blocks, right? So you can clearly see here that it's not really solving strictly consensus, because we are tossing a coin in case of ties, you know, and we're not really deciding unanimously on the same block in any case. So we came up with some interesting observation. First, that you know, committed transactions that were included in different blocks could be reordered, and this could lead to dramatic consequences, like, for example, front-running attacks, where someone, by knowing that someone is trying to acquire an asset, can leverage this information as it's to maximize his personal gain. That's one possible application of this vulnerabilities. Or by making sure that there is a disagreement, a hacker could potentially double spend, right? So this is possible in theory as well. Essentially, what it means is that at a given index, you might have multiple blocks, right? And if the network is not reliable, then these forks could be maintained for a very long period of time, which can be very dangerous. Okay, so let's dive into some vulnerabilities that are common to proof of work mechanism now. At that time, that was around 2016, 2017, we were talking with companies who were very active in the blockchain space. And one of them was R3. R3 at that time was handling a consortium of financial institutions. There were at least 50 financial companies that were part of this consortium. They were running an Ethereum network in a private environment with 50 participants. Not all of them were participating to the blockchain system at the same time, right? And as you can see on the right-hand side here, we exchanged some data with R3, and they gave us some statistics about their private test network. And you can see here that you have a list of institutions in the leftmost column. And you might recognize some banks here. For example, we can see CBA on the third line, which is the largest bank in Australia, or UBS, which is Union de Banque Suisse, which is an international bank based out of Switzerland. And you might recognize some of the banks. But anyway, these partners were teaming up to run a network of blockchain nodes, right? And what you could see is that for each of these node that was providing this blockchain network service, each of them had a particular computational power represented as mining power in the, let's say, the last column on the right, right? So it's expressed in million hashes per second. That's why the unit is mH/s. And this represents the computational power of every node. So at that time, R3 was owning, which is the top node in this list, was owning 12% of the entire mining power. You can see that not all the machines are mining, because some of them have, they don't even have a computational power list. But anyway, at that particular moment, when we took this snapshot, R3 was owning 12% of the mining power. And we decided to try to do an attack, knowing that the consensus could not be solved in the general setting, knowing that R3 was owning 12% of the mining power. We thought, okay, what could happen if one of the nodes of the blockchain networks was malicious, running Ethereum? And so we decided to split the network into two partitions of equal mining power, right? It was a theoretical approach at first, but then we did the implementation. The idea is the balance attack is for the attacker, which is represented with this red computer, to split the network, so delay communications between groups of computers in the blockchain network, such that each partition has a balanced mining power, like essentially the same mining power would be ideal for each of these partitions. Now, the malicious, the hacker will try to contribute his transaction. He will send his transaction to one partition, okay, the top partition in this case, and will contribute blocks to the bottom partition. So he will participate in trying to find new blocks, but he will send the blocks just to one half and send his transaction to the other half, right? And at the end, he will stop splitting the communication between the two partitions. And then what would happen? It could be the case that, of course, the two blockchain abstraction that were mined by different partition would be different. They have a common prefix. Maybe at the beginning they had the same genesis block, but the suffix of this directed acyclic graph of blocks is not exactly the same, right? You can see that it's not exactly the same in these two representations in yellow. In particular, there is transaction T that was sent by the malicious node only to the top partition. So T only appears in the top partition, right? They only the nodes at the top partition have the view about this transaction T. So we are bounded the deviation from the mean of the number of blocks that would be mined by each group using chain of bounds. And what we realized is that it's very easy with a very low mining power for an attacker to lead the system towards a double spending. In this case, because the hacker contributed more blocks to the bottom graph, it's more likely that the graph of blocks or the blockchain that was viewed by the bottom partition was more legitimate than the graph or the blockchain built by the top partition. In which case, when the communication is exchanged after the attack, then what will happen is that the final blockchain that will be taken as the legitimate one will be the one mined at the bottom, by the bottom partition, right? And as a result, the transaction T would vanish from the system, which means that the attacker, if he managed to convince that he has paid someone with the transaction T, can reuse the coin he has spent before in transaction T to pay something else, to buy something else, right? This is a double spending attack. And we showed through theoretical evaluation that, R3 with 12% of the mining power simply needed to delay communication for 20 minutes in this setting in order to steal assets. Okay, so that was a first interesting result that we observed. And then we went a little bit further because it was only purely theoretical. And we asked ourselves, but how do you delay messages on a network, right? It's not easy. And there is a well-known attack, which is BGP hijacking attack. So BGP is the border getaway protocol that dictates how the packets are routed over a network, right? I think the Facebook outage was due, for example, to a BGP misconfiguration or DNS problem that was related to bad BGP announcers. But anyway, there is a common attack, which is BGP hijacking, that consists in having a hacker announcing fake routes, saying, hey, if someone that is on the left would like to contact someone on the right, then you should go through me because I know a shorter route towards this other end of the network, right? So in this example, you have the attacker at the top here in red is implementing or emulating a router underneath, and he is announcing fake routes to some autonomous system, number 4 and 5 on the right, and some other autonomous system on the left, 1 and 2, such that they will send the messages towards the attacker when they want to communicate with each other. So when AS1 and 2 wants to communicate with AS4 and 5, then the messages will go through the attacker. By doing that, the attacker places himself as a man in the middle, and he can delay the messages that are exchanged between these groups of autonomous system in the network. So we did this implementation in our own network. We did a BGP hijacking attack where we were running Ethereum, and we confirmed that the attack was possible in practice. Now, an interesting learning from this is that this attack is very hard to implement on the Ethereum mainnet. And the reason is that there are a lot of nodes that are hidden behind mining pools in Ethereum. So it's very hard to know exactly which links should be cut in order to have this result. But in a private setting, then the risk exists. Okay, we looked at that, and also we talked to some industry partners. At the time, we were based in Sydney, so we talked to the Commonwealth Bank of Australia, and we learned that they were not using Ethereum proof of work in their own testnet, but they were using another variant of Ethereum that is called Ethereum based on proof of authority. Right? So if you download the software of Ethereum, there is a configuration setting that allows you not to use proof of work, but a different algorithm. It's called proof of authority. So CPA was mandated by the World Bank to implement a blockchain bond. So they were really active in the blockchain space at the time. And then learning that they were using this other variant of blockchain, we decided to investigate how this variant was working. It's very similar to what we call Byzantine fault-tolerant consensus algorithm, the kind of consensus that is used in Ethereum with proof of authority. And the reason is that they list authoritative nodes that have the authority to create new blocks. So not everyone has the right to create a new block, only a set of listed authoritative nodes or validators. So essentially you can list them and you can count them. So you know exactly the number N of validators that you have. And you know, this algorithm, proof of authority, which is implemented in Click, as Click in Geth and Aura in Parity or Open Ethereum, tolerates a minority of failures, right? So typically F greater than 2F means that you need to have more than twice as many nodes as you have faulty nodes. Right? Okay, so we did the same thing as before. We tried to understand the algorithm. That was not easy because there were no scientific papers as we're used to read that were describing this algorithm. We had to look at the code in order to understand how they were working. So I won't spend too much time on the pseudocode, but the idea here is to understand that what is important is to understand that you have sealers. These are the validators. They will seal blocks, and these are the only ones who can seal blocks. And then each node will have a current view of the blockchain, which is CI, and then they will exchange some blocks B. And every step duration, you will have a new sealer trying to seal a block, right? So there's like a periodic phase during which a new sealer, if it's his turn, will try to seal a block, right? So what will happen is that the sealers will try to seal blocks. If he cannot, then no big deal. Another sealer will seal another block after some period of time. And what will happen is that if you have a block that is followed by as many blocks as half of the number of sealers, then you can conclude that the first of this block in the series, in the blockchain, is final, right? It won't change afterwards. So that's roughly speaking how the algorithm works. So we did an attack. The attack is very similar to the balance attack, except that it applies to Ethereum proof of authority. And we're essentially, we call it the attack of the clone because here you have a malicious machine, a server, that will clone himself. It means they will use two different machines with the same public and private key pair. So it will authenticate the same way to the network, but from two different machines. And by doing that and partitioning the network in two halves, as you can see, putting on one side sealer 3, 5, 7, 9, and on the other side, sealer 2, 4, 6, and 8, it can do a double spanning attack. It will pretend to be sealer 1 sitting on both partitions. The idea is very similar to before in the sense that it will wait, you know, preventing the communication between these two partitions for long enough such that sufficiently many blocks will be appended after the block that contains the attacker transaction. Once this happened, the network would be convinced that the transaction has been committed. But once the communication resumes between the two partitions, then the sealers will realize that they have done a mistake. They accepted two conflicting transactions while they were not supposed to do so. And these are transactions TX1 and TX2 in this example. Okay, so again, the attacker will be able to have a double spend by being the only malicious server node in the system, right? So you don't need to have more than a minority of malicious sealer in order to achieve this result, unfortunately. So when we discovered that, we contacted the Ethereum community, the developer communities of Geth and Ethereum, of Geth and Parity. They both confirmed the cause of the effect of the attacks. We also presented that as the Ethereum development conference. This is my PhD student, Parinia, who came up with the attack, who is presenting on this picture. And yeah, we generalized this result and trying to see what was the ratio between the malicious sealer and the sealers in order to have an algorithm that would violate agreement or violate termination. And when you violate agreement, you affect safety. When you violate termination, you affect liveness. So we were looking at where the algorithm would be safe but not live, or live but not safe, and so on. Okay, so I think now that we have reached this stage in the presentation, now I think you have an understanding that the network delays can have a huge impact on the consistency of the blockchain network. And this can have dramatic consequences, having unexpected network delays. So there is this assumption that is quite realistic for the internet, for example, which is the following. You assume that you know, there is this delay that cannot be predicted for a message to reach its destination on internet. But it's acceptable to assume that if you keep sending and sending again and again the same message, then, you know, it might not work at the beginning, but, you know, internet will be eventually fixed and the message will go through and reach its destination at some point. So it's a different, it's an assumption that is realistic, let's say, because it's, you know, that internet may be broken at some point, but eventually, you know, that, you know, internet will be fixed. And it happens sometimes that Australia has a hard time communicating with other continents. For example, there was an earthquake in Hong Kong that impacted some backbone and disconnected Australia, or at least impacted the delay of transmission of messages. But at some point, you know, the other routes were taken for communication and everything went back to order. So it's realistic to assume that we have that. And this assumption is usually called in distributed computing as partial synchrony, right? We know that there is a bound on the delay of messages. We just don't know this bound, right? So we know that, you know, eventually the communication will go through, even though we might be affected for potentially unexpectedly long time, right? And what we realized is that the classic blockchains like Bitcoin and Ethereum were not making this assumption, right? They were making a stronger assumption, which is synchrony, that there is a known bound on the delay of messages. If you violate this bound, then things can go wrong. If someone can partition the network for too long, then you might have double spending, right? So the idea here, in order to cope with this kind of double spending attacks, is to tolerate partial, to come up with a solution that assumes partial synchrony, but not pure synchrony, right? So that's a big distinction. Okay, so there are a lot of consensus solutions that you can find in the literature that already solve the consensus problem, even though you have Byzantine failures, and assuming only partial synchrony, right? And I can cite PBFT, Ziziva, BFT Smart, Fab, Alif, Aardvark. There are many of them. And these were designed starting from 1999. You know, I mean, the seminal work, PBFT, was published around these years, right? So you can see that it's older than blockchain technologies. But these solutions were essentially designed for local area networks, right? So PBFT originally was presented for a network file system application running on 4 machines, right? So it was really for local area network, not a large network like what Bitcoin is using. And of course, in the blockchain context, you would like to have consensus that is Byzantine fault tolerant, that only assumes partial synchrony, but that should work at very large scale, right? So that leads to the second part of my talk, which is about scalability. If you can tolerate partial synchrony, you won't have the problem of security that I've presented before. But now you have to scale, right? So how do you take this off-the-shelf solution from the 2000s and you try to make it work in a blockchain context? That's the question I'm trying to answer here. Most of these consensus algorithms that were inspired somehow by the seminal practical Byzantine fault tolerant consensus algorithm follow the same model, in the sense that you have a leader that will try to impose its value to the rest of the system. So the way you come to an agreement is by having one particular node saying, here's my block, please accept it as the next block in the blockchain, right? So this is usually how it works. And if the leader fails, or if it's too slow, then another leader will be elected. But at the end of the day, the leader will try to impose its block to the rest of the system, or its value, right? This is how this family of protocols work, right? So you can see here the message pattern of the PBFT consensus algorithm, where the request coming from a client reaches the leader exchange with all the other nodes, get some answers from them, making sure that they've heard about what is said before, re-exchanges message, resends messages until there's a commit, at which point the client can be notified that the agreement is reached, right? But what is important here is that the leader has to send a lot of messages to everyone because he wants to convince them. Right, so this is the long version of the PBFT paper, was published a few years later in ACM Transaction on Computing System. Okay, so what I want to illustrate here is that this leader-based model might not be well suited for the blockchain space. Okay, we know that as a consensus algorithm that tolerates partial synchrony, it will cope with the vulnerabilities that I've mentioned earlier. But if it's leader-based, can it really scale to a very large network? Intuitively, the leader could act as a bottleneck in your system, right? If it has to, convince thousands of nodes, it's going to be tricky for him to do so, because he will have to send messages to all these nodes one after the other. So that's the underlying idea. But if we could come up with something that is more a symmetric algorithm, where there's no particular node that should act as a leader, no one is trying to convince everyone, everyone is just talking about what he is proposing, and everyone is trying to agree on everything at once, then you can think of maybe a better approach for scalability. So consider a consensus algorithm that decides a set of transactions of capital B bits. Okay? Capital B is like the amount of bits that this block contains, right? So it's like a block, right, that we're proposing. And we want to decide upon a block that contains these transactions. We want to compare the performance of a typical leader-based approach and a typical leaderless approach. Of course, these two approaches will be extremely simplified for the sake of the presentation. In a leader-based algorithm, the set of transactions is proposed by the leader. In a leaderless algorithm, the set of transactions will be proposed by everyone. There is no leader that tries to convince about a particular block. So what is the transmission time of a block in the leader-based consensus? And let's have an example. Here you have 4 nodes, right? These are servers connected via internet, and so it's not a local area network, right? We don't have a broadcast primitive at the IP level, right? This is important. This is the internet. This is a wide area network. And you have these machines that are trying to communicate with each other. They have a download rate. Each machine I has a download rate DI and an upload rate UI, right? The leader is at the bottom. It has download rate D1 and upload rate U1, okay? And he wants to transmit this big block that contains B bits, right? That is next to him, as you can see in dark gray. So let this process or node one, that is the leader, and consider that the other nodes or processes are followers, right? They're just trying to get this block. Let UI be the upload capacity of process I and DI the download capacity, as I said before. Now the time at P that is taken in order to transmit this block, this set of transactions from the leader to all the other processes that are followers will be the maximum between the time for the leader to upload n times B bits. Why? Because over the internet, if you want to broadcast a block, you have to send it to each destination, one after the other, right? It means that the time it can take is n times sending B bits through the upload capacity of the leader, right? So it will take n times B divided by U1 time. Or it can take the time for the follower with the lowest download rate to download these big blocks. This will be the minimum among all the download link capacity between D2 to Dn, okay, to download B bits, which is B divided by the minimum of the Di, right? And this would lead to P equals the maximum between two things, right? And both of these things will depend on this block B and the number of nodes that you have in the system, right? So essentially what I'm saying is that here, the time it takes for the leader to transmit a block to all the other nodes in the network is the maximum between the time it takes for the leader to upload it and the time it takes for the slowest downloader to download, right? So you can clearly see that the maximum between these two expressions is lower bounded by n times B, right? The number of nodes times the amount of information that should be transmitted. And what is important here is that it depends on number of nodes. And I can even say that it's omega NB, right? So it's like lower bounded by n times B to a constant multiplicative factor. But if you are in the case where you have no leaders, you're in a leaderless case, the idea is different. You can have this block that you want to decide of B bits, but actually it consists of something that is split among all the nodes. And everyone is actually proposing 1/n of all the bits of this block, right? Each of them is proposing to the consensus his own share of the decision, right? So in this particular example, each of the machine will send B divided by n instead of having the leader sending this bigger block B. The time it takes to exchange these sets of transactions is the maximum of the time for the slowest process to upload B over n bits, and the time for the slowest process to download B bits, right? Because he has to download from different nodes. So overall, the time it will take with the leaderless algorithm will be the maximum of B over n divided by the minimum upload capacity and P divided by the minimum among all the download capacity, which is only proportional to B. Okay, it's O of P. So it turns out that if you want to compare the time it will take for a leader-based algorithm to transmit its block, you will see that it's linear in the number of nodes that you have in the system. Now, if you have a leaderless approach where everyone is trying to share its proposal in order to get a unique decision, then it will not depend on the number of nodes in the system, and it will be constant. And that makes a big difference in order to scale. So you can think about why the typical leader-based consensus algorithm will not scale to a very large system because they are relying on the leader that will have to do more and more work as the number of nodes in the system grows. Okay, so it's again a very simplistic analysis of what's happening, but in practice we have also observed that the typical leader based algorithms do not scale. Like we know, for example, there are consensus algorithms that tries to minimize the bit complexity, but what we realize is that they still have a hard time scaling, which means that the performance tend to decrease as you increase the number of nodes in the system, which is kind of unavoidable if you have a leader. Okay, so without a leader, the load is more balanced. There is no need for a special node to sign messages. There is no need for the leader to receive and send a large volume of messages, and it can remove the bottleneck. There are some other things that I did not mention, but yeah, we won't go into too many details today. So how do we reach large scale? And that's going to be the last part of my talk. One way is to try to assume partial synchrony, because you would like not to have the vulnerabilities that we've mentioned before, but also to try to adopt a more leaderless algorithm. Yeah, one thing I didn't mention is that the traditional consensus problem is slightly modified when you consider that what you're deciding is no longer one of the value that was proposed, but it's actually the combination of all the values that were proposed. That's just a parenthesis. It doesn't change fundamentally the problem. So we came up with a democratic Byzantine fault-tolerant algorithm that was assuming partial synchrony, and that was leaderless. So the idea of being democratic means that you don't have some node that is trying to impose its block to the rest of the system. Instead, you have every node proposing a set of transactions, and the decision is like the combination of what was proposed. We build a blockchain on top of this consensus algorithm that we called Red Belly blockchain. It tolerates the delays. Of course, at some point, communication has to go through, but we don't know the time it will take for a message to be received. So we believe that it's a realistic assumption. It remains safe during network attacks. So even though you have the network that is cut and partitioned during this time, there is no double spending because we don't commit any transaction if we have a partition, right? So only termination will be affected. It's like favoring consistency over availability for those who know the CAP theorem. Because it's leaderless, it scales, right? In the sense that we can leverage the resources of more and more nodes, and the performance can go up and up as we add more resources to the system. And one interesting thing that we have done very recently was to formally verify the consensus. So the binary consensus part that is within Red Belly blockchain was formally verified with model checking, parameterized model checking that allows you to verify for any parameter NNT. It's part of a separate paper. So we tested this approach, and we realized that okay, and in a single data center, which is not realistic at all for a blockchain, but we really wanted to stress test the performance of our system. We realized that we could get very good performance, and that the design was scalable because we were adding more and more nodes from 20, as you can see here on the x-axis, from 20 to 260. The throughput was going up and up and up. We tested 280, 300, and then it was flattening out. So keeping being roughly the same, but not dropping dramatically and not increasing anymore, right? So we were limited by the bandwidth. But this is what we call scalability, in the sense that we don't, the performance is either preserved or enhanced as we increase the scale of the system. So this was done on powerful machines in a single data center. And then later on, we said, okay, let's do something more realistic. We deployed 1,000 virtual machines on AWS. At the time, we only had 14 availability zones at our disposal. So we spread the nodes in these zones. You can see that there are more machines here and there. So it's between 160 machines per availability zones. An availability zone is like a data center that belongs to Amazon. And because we really wanted to use links that were not just on the local area network, right, to test the performance. And what we observed was that the average latency for committing a transaction was 3 seconds. And the nice thing, of course, of this strict consensus resolution is that once something is, a new block is appended, then it's final, right? There is no fork. So you don't have to wait until there's a fork resolution. It's immediately final. So that was a very interesting result. And this is it. So to conclude, classic blockchains are not tolerant to unexpected delays, and this can lead to dramatic consequences. One can use partial synchronous consensus to solve this problem, to make sure you tolerate unexpected delays. Most partially synchronous consensus are leader-based. They are heavily inspired by PBFT. And for blockchain, we believe that leaderless is a very interesting property because it allows to really scale the performance and really leverage the resources as we add more nodes to the system. So we've developed Readily blockchain for that we believe achieves some high level of security while still offering some level of scalability. So here are some references about the papers that I've mentioned during my talk, and I would like to mention this massive open online course that I designed with University of Sydney that also reuses some of the content that I presented in this talk. Thank you for your attention.
Thank you very much, Vincent, for your talk. I see there are some questions in the, if anybody has questions, I believe the way is to type them in the banner of questions and answers. I see one by Isaac Lara that asks, are game theory and mechanism design useful to study or address some of the security issues you have mentioned?
Yeah, that's a very interesting question. I'm not a game theoretician. I'm more of a distributed computing, community. But I really like game theory, and I think it has very important consequences for blockchain. In particular, there is something that I didn't discuss, and I've been working with some students in Sydney and in Lausanne. It's a topic called accountability. And this is something that is completely absent from the classic blockchain. Accountability is the idea that you can hold the participant responsible for its actions. And if you look at Bitcoin and Ethereum and double spending in general, if you manage to double spend when you do forks, it means that the transactions where you promised that you would pay a merchant vanishes from the system, and it vanishes with the entire branch, which means that a posteriori, there's no way to go back in time and say, oh, who double spent in the past? Because the trace where you double spend, the transaction where you double spend, by definition, are not there anymore. They vanished from the system. That's why you managed to double spend. So there is no way to trace or to prove that someone is guilty in classic blockchains. What I found very interesting is this, in this notion of accountability, is that there are now algorithms that make sure that if there is a fork, then we have a way to generate undeniable proof of guilt, which means, okay, if everything goes fine because there is not enough, or the coalition of malicious players is not big enough, then we have consensus. But if this coalition grows too big and we cannot ensure consensus anymore because it exceeds n/3, for example, then at least we have one guarantee with accountability, which is we know for sure, we know who is guilty. And this, I think, bridges the idea between consensus, this idea of accountable consensus, bridges the idea of consensus and something that would lead to a game theoretical model where the players are rational. Because if they're rational, and I think most of the people are rational, they're not just Byzantine, right? Then they would be disincentivized to misbehave if someone can catch them. I hope this answered the question.
Okay, thank you, Vincent. Another question by Peter Kuznetsov. Is there a formal definition of a leaderless protocol? And if there is, what would be the best reference?
Yes, actually, there is this paper by several students at EPFL I contributed to. It's called the Leaderless Consensus. It was published at ICDCS 2021. And the formal definition is slightly different than what we have used here. The definition says roughly that if an algorithm is leaderless, typically a consensus algorithm is leaderless, if you manage to terminate, even though one process is interrupted at a time, right? So you can construct an execution where there is always one process that is interrupted, doing nothing for some amount of time, right? It could be a different process at different moment. But if your consensus algorithm terminates in this execution, then you can say that it's leaderless, because it means that it doesn't need the progress of a single process in order to reach termination. It's a different property than what I informally stated here, because the property was more about a leader sending to all versus everyone exchanging in an all-to-all fashion.
Yeah, thank you. So, for example, a system like Algorand, how would you classify it?
That's a good question. I think Algorand also uses a reduction from the multi-value consensus to the binary consensus. And I need to look into BA star a little bit more. But yeah, I need to look at it more. I'm not sure it would be leaderless according to the ICDCS definition, but I need to look into it more.
Yeah, and the related question is, what role plays linearizability in leaderless protocols?
What's the relation with linearizability?
Are they linearizable or some other consistency property they satisfy?
That's an interesting question. Yeah, so for the linearizability, this is what we want to ensure, right? We have a total order on the blocks. We really want to make sure that concurrent blocks, or blocks that are not proposed concurrently will end up in the right order in this total order. So I think we have some kind of linearizability when we talk about consistency. A recent property that has been defined that relates a little bit to linearizability was part of a paper published at OSDI in 2020. And the idea is, it's a definition of ordered linearizability that I think makes a lot of sense in the blockchain space. It essentially means that despite a coalition of Byzantine nodes, this coalition cannot dictate the order in which transaction will be ordered in the total order in blockchain. And I think it's a very interesting property, because the blockchain anomaly and the front-running attacks that I've mentioned at the beginning are the motivation to introduce this kind of ordered linearizability property. If your system ensures ordered linearizability, it means that there will be mitigation to front-running attacks, because a coalition of malicious processes will not be able to reorder the transaction the way they want.
I was asking the question because I thought I got the intuition that since you can combine in the agreement value, in the agreed value inputs of different processes, then it would not be linearizable, because in some sense, inputs that were proposed concurrently are combined into the same agreed upon value. So I thought it would be more related to other properties like interval linearizability or set linearizability that allow to order concurrently operations by different processes.
I see what you mean. Yeah, you're right in the sense that we don't have a very strict order imposed on the transactions that will be decided in the same block. We're using, let's say, a lexicographical order would be a naive approach, right? But then it could be the case that a transaction that is submitted before another could get ordered after. But still, these transactions are concurrent, right?
Yeah.
They're concurrent, but I agree that the concurrent transaction can be reordered. But as long as the system didn't say, okay, your transaction is act and committed, like acknowledged and committed, I believe this is acceptable. What we will guarantee is that if you submit a transaction and then the system tells you it's committed, and then there's another transaction that is being submitted, then this other transaction will be ordered after. So we have this real-time precedence, which is still some nice property, but I agree with you that maybe we could have a stronger property. It would be interesting to implement even a stronger property. And I'm wondering whether it doesn't relate to ordered linearizability in this case. Because it's like receiving transaction and deciding that the order that matters is the order with which the correct nodes perceive the transaction. So if all the correct nodes perceive one transaction before another, then these two transactions should be ordered like that, right? It's not about ordered linearizability tries to impose an order even on concurrent transactions.
Yeah. Yes, many interesting issues. There are more questions, but I'm afraid we cannot go too much over time, even if we started a little bit later. But let's thanks Vincent for such a nice and interesting talk, and I'm sure we can continue discussing by mail or later on during the day. Thank you, Vincent, very much.